Good day, folks. This is video number 6, and it's in the motion design playlist which deals with dynamic problems. It's all coming from 3D Experience platform. It's a very simple torque loading, and the situation is shown here. We have a disk with the given dimensions, and it's with certain material properties that I'm going to show you in a minute. And this is being under the application of a torque of this magnitude. What we like to do is to basically solve the problem as a dynamic one and find the velocity, acceleration, etc. of the disk. Now, I'm assuming that the disk is made out of steel, and the default density in 3D Experiences database for steel is this number, 7,770 kilogram per meter cube. Now, if you don't assign properties to a dynamic problem in motion design, it will use this value, this density, to calculate the mass of the object, okay? So if you don't do anything, as you'll see in a minute, the mass of that object is going to be 152.6 kilogram. Now, when you're dealing with torque problems, one of the things that you have to calculate when it comes to hand calculation is the basically moment of inertia about the axis of rotation, which is called I-axial. And if you go to a strength of material book, you will see that this IZ, mr squared, 1/2 mr squared, is given explicitly. You also have moment of inertia about the other two directions, which are called transverse directions, but in a pure torque problem like that, it doesn't come into the picture. But anyway, let's move on. The simulation is going to be done over 10 seconds. Now, elementary strength of material or dynamic tells you that torque is equal to I times alpha or I times omega dot. And if you have the torque, and we do, and you have the axial moment of inertia, then you can find the ratio, and you're going to get omega dot, which is the angular acceleration, by the way. And if it's a constant, as it is in this case, then by integrating it, the angular velocity changes linearly and, of course, increases as a function of time. Now, these are, as I said, these are called angular acceleration. And if you plot omega t, angular velocity, as a function of time, you get a linear function like that. It starts at 0, assuming that the disk was at 0 velocity initially. And in the event that you have initial conditions, please watch the previous video. I think it's video number 5, which I show you how to incorporate the initial conditions. But anyway, because we don't have any initial condition, everything starts from rest. This is going to be the plot of the angular velocity. And we're going to check our calculations against this. So at the end of 10 seconds, roughly 419 rad per second. Now, how do we apply a torque? Well, first of all, when you are in the mechanism tab, these are some of the things that you see, and there is an applied load here. And when you select the applied load, you have two options: either apply force or torque. In my case, I'm going to be doing torque. So when you select this, of course, these numbers are going to change to Newton meter, etc. Now, I will show you what happens when you model this problem. Notice that when you click on the body being that disk that I'm going to make in a minute, you're going to get the moment of inertia, mass moment of inertia of that disk. Okay, now first of all, the mass of it, notice that it's right here, 152.56, which is using the density of steel by default. And then if you plug in those formulas that I had, the numbers are going to be fairly close. Notice that these products of inertia are 0 because it's a basically symmetric problem. Disk is a symmetric object. Okay, it has 3 planes of symmetry, so these products of inertia are 0. But anyway, it's a good check. And there are other ways of doing it. Now, in this problem, I can do it either as a free disk in space, which is torqued. That's one way of doing it. The other option is to create a revolute joint and apply the torque to that disk. So let's go ahead and do that. This is the approach that I'm going to take initially. So we go here. Let me insert, first of all, the disk. Insert 3D part. This is going to be my disk. I'm going to change this thing to say disk. Okay, let's go make it. Double click. Go into part design, and on that plane, I will sketch a circle of radius 0.25 meters. 0.25 meters. Okay. And then we pad it by 0.1, the height of the disk. There we are. And now because I'm going to do this thing as a revolute joint, although it can be done as a free spinning disk, as a revolute joint, I'm going to create a base here just to make it look nicer. So right click properties, insert another 3D part, and I'm going to call this thing the fixed base. Let me see now, properties, fixed base. Okay, let's do it here too. Fixed base. All right, let's go make it. Double click. All it is a cylinder. So for example, on that plane, I will sketch. And the circle here. Actually, dimension it doesn't matter because it actually stays stationary. So I'm going to pad this thing, or I'm going to flip it just so that I can see it better. Let me make this thing 0.2, see how it looks like. Yeah. So there is my fixed base. As I said, this is not going to do anything. So let me actually do the following. Let me change the color of that for no particular reason. All right. First of all, I don't need these things, so I might as well hide them. Everything down here. Hide. Okay, good. Now let's, because this is an assembly, let's apply assembly constraints. We go all the way to the top, and then we can find, I click on the assembly tab, and then here are the engineering connections. So let's fix the base right there. Okay. There we are. Okay, good. And now we're going to create a revolute joint between the disk and fixed disk, the disk and the fixed base. Revolute. There's 10 different templates. It doesn't matter which one you use. I'll use this last one. So the axis of this and the axis of that, and the plane of this and the plane of that. And I don't need this last set of boxes. And then we say, okay, so a revolute joint has been created right there. Let me update necessary. Okay, good. Now notice that I did not specify any materials, okay, to any of these pieces. So now I'm going to go to motion design. By the way, remember these problems I have also done using the mechanical systems experience and mechanical systems design playlists, and you can do that. But this motion design is something else. It's a different application. So motion design, and it's going to create our mechanism for us, which is fine. Nothing, no big deal. All right. So gravity is active. I don't want to. I want to deactivate it. Right click, put the cursor there. Right click, deactivate it, or you can put gravity or gravitational constant 0. If you double click on the gravity, you're going to get gravity in the direction z minus 9.8. You can make it 0 or deactivate it. And notice that there is a joint, there is a revolute joint. One more thing I want to show you, and that is if you open up the body, notice that the ground has been automatically created for you. I didn't do this. I did the fixed disk right there. And if you double click on the fixed disk, this pops up. This gives you the mass properties of that fixed disk, but you can leave it the way it is. It really doesn't matter. Or if you insist that, okay, if it's not moving, I should not have mass properties for it, which is true, but it's not using it, you can click on this so that it becomes a massless. Okay? It's really up to you. It doesn't matter. Oh, sorry, that's the wrong one. That's the wrong one. The one I wanted was fixed disk. That's the one that I wanted massless. You can do massless and it's going to be gone. Okay? But if you insist to have mass for it, there is the value and it's not going to participate anyway. But I'm going to make it rigid massless. Doesn't matter. Good, good. That's pretty much it. So incidentally, you can, let's see, if we go to, for example, if you go to a mechanism and there's this kinematics player, and you see that there's going to be a tab here which shows you that this is actually rotating, spinning. So reset it and get out. Now, where's the torque? So if you look at the mechanism, you go and find the torque applied load right there. This is what I had in the PowerPoint. Click on it. I don't want the force, I want the torque. And you have several, what we can apply, for example, in the direction Z, I want 200, right? Whether you put plus 200 or minus 200, it rotate this one way or other one. In our case, it doesn't matter. And the application point, if I select the uh, uh, the disk, it won't let you pick the disk here, but you can select it from the, if you expand it, you can select it from the markers. These are the markers, right there. Notice that something was picked here, and you say okay. And that's pretty much it. There's nothing else to do. You're done. Now, if you go to simulation and run it, wait until this says 100% successful, and then you go to we go to results, and let's plot angular velocity. Okay, so you click on the 2D plot. It says what is it that you want to plot? Well, I want to plot angular velocity of the disk. So first of all, expand this thing so that you get the disk. It says what is it that you want to plot? So let's say angular velocity about the z direction, and I better get that straight line starting from 0 going to roughly 400. Yeah. The only thing is that this is radians per second. Let me see for a second. 209 radians per, oh, this is going over, yeah, that's why it's going over 5-second intervals. So I forgot to change the duration of the simulation. Let me go back here to this uh, step and change it to 10 seconds. No wonder it went only halfway. Okay, and then run it again. Okay, finished. Go to results, 2D plot, and select the disk and angular velocity in the Z direction, and it's going to go from 0 to 410, roughly, yeah, 419 rad per second. You can also add acceleration, angular acceleration to it, which is going to be a constant, incidentally, right here. If I uncheck that, angular velocity, yeah, right here. Well, this is velocity. Let me uncheck that. Okay, let's make sure we get the right thing, because I don't like this acceleration. This acceleration in the Z direction, and angular velocity, angular acceleration. Oh, angular acceleration. This is the one that I wanted, not that one. And that's going to be 41, which is pretty much what we got here. Angular acceleration 41.9. All right, folks. So that's pretty much it. If you want, you can also solve this problem as a freely rotating disk without actually making that stand and the revolute join, and it'll work fine. I leave it to you if you're interested. It's very simple. Okay.